Hey there. I'm really sorry I couldn't meet you guys for class today. My wife almost passed out again, and we're having health issues. So I got to take care of that. And I'm sorry I can't people today, but I'm gonna give you the lecture I would have. Conditional probability. If A and B are events with the probability of B not equal to 0, then the probability of A given B is, all right, so this little line means given. A given B is the probability of the intersection divided by the probability of B. So what's the probability of a Seahawks game getting canceled given that it's raining in Seattle? It's still going to be 0 because they play in the rain. But that's the type of thing. If this is already happening, what's the probability that this other thing does? Multiplication principle for conditional probability, really all we're doing is taking this formula and multiplying both sides by P of B. So we can find the value of the intersection. We can find any of these values that we want to. Keep in mind that the intersection is just equal to P of A times P of B if the events are independent. All right, if they are independent. And the whole idea of the intersection, the probability of the intersection being probability of A times probability of B, we can extend that. It can go with more intersections. You can intersect 7 different sets, and we'll end up multiplying the probabilities to find the probability of the whole intersection. So if we want to know if two events A and B are independent, we find all these values and make sure that this equation matches up. All right, so let's compute the indicated quantity, and each time we do it, I am going to include the formula. Probability of A given B is the probability of the intersection divided by the probability of B. Always this given is always your denominator. Intersection of the two is always your numerator. So we know that the probability of A given B is the intersection divided by the probability of B. Multiply both of these by 10, and we get 4/5, or 0.8. I'm going to go with 0.8 in this case. They gave me the values as decimals, so I'm going to answer as decimals as long as my decimals terminate, right? We don't want them repeating. Compute the indicated quantity. We're looking at the same formula. But this time we're trying to find that denominator. So I might set up my formula as 0.4 equals 0.3 divided by, I'm going to call it x, because P of B is, that's peanut butter. That's not a variable. I'll multiply both sides by x, and then divide by 0.4. And to simplify, both of these are tenths, so we multiply both the numerator and denominator by 10. Or just use your calculator on this step. And there's a 75% chance that B happens if the probability of A given B is 0.4 and the probability of the intersection is 0.3. And we can find that value through a little bit of arithmetic, but it always comes back to this formula. Find the conditional probability of the event indicated when 2 fair die, so these are distinguishable, are rolled. Okay, 1 red and 1 green. Given is our B, given that the green is 1 or 4. And we want, let me see, we're going to call A to be the sum is 7. And what we're looking for is the probability of A given B. So we have to calculate the probability of the intersection divided by the probability of B. All right, so the probability of the intersection. The intersection will be sum of 7 with a green, a 1 or 4. So we have 1 red and 1 green. Let's write them down. Let's see what we got here. Let's call that one red. Let's call this one green. There we go. So the green is a 1. Well, wasn't that fun? Let's bring it back. I wouldn't want you to think we weren't actually in class here. Right? Same thing happens in class. All right, save it. All right, so if the green is a 1, the red has to be a 6 to get 7. If the green one is a 4, the red one has to be a 3 to get 7, right? A sum of 7, and the green one has to be a 1 or a 4. There's no other red number that we can add to 1 to make 7. There's no other red number we can add to 1 to get, add to 4, excuse me, to get 7 either. Wow, I can't do something. And so there's only 2 possibilities. And we know that because they're distinguishable, the number in the sample space is 36. So the probability of A intersect B, excuse me, is 2 out of 36. That's not where that goes, because that is my intersection. So let's look at P of B, and it would be silly of me to do this in a red marker. So probability of B is what we have to look for now. A green 1 can go with 6 reds, right? You can go with a red 1, a red 2, a red 3, and so on. The green 4 can go also with 6 reds. So there are 12 total outcomes that have a green 1 or a green 4. So that's 12 out of 36. But check this out. When we divide by a fraction, we can multiply by the reciprocal. 36 is cancel out. 2 over 12. I was thinking ahead. All right, multiply straight across after we cancel. 2 over 12, which is 1/6. Because this decimal is horrible, it's like 1/6. 0.166666666. It doesn't tell you how to round, so you don't round. You leave it as 1/6. All right, I'm going to hit save. We're going to do number 7 together. It's one of those walkthroughs. So let's take us over here. All right, let's begin. Find the conditional probability of the given event when 2 fair die are rolled. The red one is 3, given that the green one is 3. All right, so it's going to be very similar, only a little less going on in terms of the steps. Let's take a look. This is super helpful for the problem we just did. Recall that for the experiment of rolling 2 die, there are 36 possible elements. Since both die are fair, all outcomes are equally likely. So because probabilities are never negative, and the sum of all probabilities of all outcomes in a sample space must be 1, the probability of any one of the 36 equally outcomes is 1 in 36, right? Any one of these has a 1 in 36 chance of happening. Okay, the events under consideration. The face-up number on the red, which we're calling the first die, is 3, and the face-up number on the green die is 3. To find this probability, we use the conditional probability formula. So the red one is 3, given that the green one is 3. So to do so, we need to find both the probability of the intersection and the probability of B. To find the first of these, the intersection, note that the event the intersection is, right, what happens on red? The red die is a 3. What happens on B? Green die is a 3. So the intersection is and, right? It's like the A just needs a little crossbar right here, and you can make an A for and. There we go, and. So it's going to be this one, all right? Intersection and. Intersection and. So fantastic. In order to do that, we know that out of the 36 possible we're looking at outcomes. There's only one where this occurs. That's 3/3. So the probability of A intersect B is 1/36 because there's only one possibility. However, we now find the probability of B that the probability of the green or the second die shows a 3. So the second die showing a 3, the first die could be 1, 2, 3, 4, 5, or 6. There are 6 outcomes, each with a probability of 1 over 36. And if I add 1 to itself 6 times, we get a 6 over 36. All right, fantastic. Remember, you could always pause or rewind if you need to hear that again. That's the beauty of recording. We found that the intersection is 1/36, and the probability of the probability of the intersection is 1/36, and the probability of B is 6 over 36. Using the conditional probability, we can find that the probability that the red die shows a 3 given the green die shows a 3, 1 over 36 divided by 6 over 36. Did you notice over here? There we go. That when we're both denominators are 36 here, they end up canceling out. So my 36s are going to cancel out, and this answer is also 1/6. These answers are not always 1/6. All right, it just so happens that 2 in a row were. All right, so we completed that. Good job. Way to work through it. There's not much to do on that one, so maybe I'll just put it there. All right, this one. I'm not going to say much, but that is something that you will definitely want to know. We'll see if that comes back. I have no idea what it does. Here we go. Factor trees are awesome, and probability trees are even more awesome. So what we need to do at each level, all right, and here's a level, and then here's a level, and then we could go on from here if we wanted to, but everything here from the start to this end, this has to add up to 0.1. No, it doesn't. It has to add up to 1.0. So if I already have 0.3, I need 0.7 in order to add up to 1.0. Same thing in here. In between these two lines, everything below, oh, that's not true. That's not true. Let's make this true. This little tree right here needs to be a 1.0. This little tree right here needs to be a 1.0. So if I already have 0.2, I need 0.8. And then the coolest thing comes right here. And I know, mathematician cool, but still. This is A and then C. A and then D. B and then C. B and then D. So if I want to find the probabilities, all I'm going to do is multiply. 0.3 times 0.5. We know 3 times 5 is 15. There were 2 decimals. So 2 decimals. 0.3 times 0.5, still going to be the same value. 0.7 times 0.2, 7 times 2 is 14. There were 2 decimal places. Remember back in elementary school when we used to do this by hand? 0.7 times 0.8. 7 times 8 is 56. 56 with 2 decimal places, that's 0.56. But check this out. 56 plus 14, that's 60, 70, 85, 100. This is 100 or a 1.0 at the end, right? This whole thing adds up to a 1.0. Crazy cool. Right? And number 9 is exactly the same, right? It's the same idea. I don't know. This might be on a quiz, maybe. Maybe then it's also on an exam. Maybe. 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 Hint, hint. All right, scrolling on. Let's look at number 10. Let's make it a little bit bigger in case you're doing the wrong thing and using your phone to watch this. Hey, you got to do what you got to do, right? In a certain year, the probability that a person in the United States would declare personal bankruptcy was 0.003. Oof. All right, too many words. Probability of bankruptcy Well, that's good, but when you're looking at 350 million people, that kind of sucks too. The probability that a person in the United States would declare personal bankruptcy and had recently experienced a Big 3 event. So probability of bankruptcy and or intersect a Big 3 was 0.002. What was the probability that a person had recently experienced one of the Big 3 given that she had declared personal bankruptcy? I don't know why it's got to be a she. Why is we got to... No, I'm just kidding. You got to pick... You got to pick. That's what they should be doing in all of these problems. Everything else was general. Let's make that they. Okay. So let's call this X. Let's not call it a question mark. It's hard to do work with a question mark. Let's call it X. All right. So I'm going to let bankruptcy be B. All right. So we'll let this one be P of B. This one is the probability of B intersect A. And this is the probability of A given B. So we have everything we need because we know the formula. And keep in mind, this is the same as B intersect A. Intersection is commutative, meaning you could do it in either order. So a bankruptcy is 0.003. The intersection is 0.002. That's 2/3. Round your answer to 4 decimal places. 0.6667 would be our answer. All right, so taking the words and putting it into math terms has always been one of the hardest problems, because every single one of you, given a formula and values, you can solve this, right? The math is the easy part. The hard part is right here, taking all of these words and putting it into relevant math terms. So that's something you should definitely work on. And I think bankruptcy is one of the worst, or one of the weirdest words that I've had to write down lately. So I said, let's do number 12. I don't want to. I changed my mind. We're gonna remove that. I apologize. It's due to time and mental fatigue. Let's look at number 14. The table shows the results of a survey of 100 authors of a publishing company. All right, so the 100 authors is our total. But we may never use that total. All right, just because it's the total doesn't mean it's going to be used. Here we go. We want to, let's use blue. All right, find the conditional probability. So given that she is established, so I only care about this group right here. Given that she is established, there are 65 established writers. Of those 65 established writers, ooh, I like that color better. Of those 65 established writers, I want the author to be unsuccessful. And this is a fantastic way of doing it, and that's the answer, 45 over 65, but we would probably reduce this somehow. We could reduce it pretty easily. That's 5 times 9 over 5 times 13. Yes. So that's 9/13. But we could also do this like what I call the long way. All right, the long way is using this formula. Okay, that's it. That's done. That's how I do this problem every time I have to do this problem. That's how I would have shown you in the classroom. That's how I would have shown you if this was a live interactive video. But we could also do probability of A intersect B is 45 over 100. Probability of B is established, is 65 over 100. But when we divide a fraction by a fraction, we multiply by that second fraction instead. And so either way, you're going to get the same answer. I like taking this given as my denominator, the total given. And when it comes to these tables, I don't know, just saying, pay attention to these tables. You've seen them in every section, I believe, in chapter 7 and 8, or at least everyone in chapter 8. Leads me to believe that these might be important on, say, a quiz, and therefore an exam, and possibly a final exam. All right, that's it, which leaves like no time for questions. But hit me up on WebAssign and use the Ask Your Teacher. I will be checking throughout the rest of the week and into next week. Next week, currently, I have every plan to be on campus next week. But it depends on the events of today. I've got to go now. I've got to go take care of my spouse and make sure everything's cool. I do not wish this COVID on anyone. Take care of yourselves. If you're going to be around family from out of town, she's completely vaccinated. I'm just saying, she's careful. She wears masks everywhere she goes. She's vaccinated. She's still got it. So be careful and take care of yourselves. And if you need a way out, if your family's getting to you, use me as an excuse. Tell them, I'm sorry, my math professor's a jerk. I have to get this done by tomorrow. She doesn't believe in holidays. Use me. I don't care. Take care of yourselves. Bye, guys.